Welcome to solverfy.
Okay, so for this problem, we have a loop and a solenoid. So I'll go ahead and draw it. And I'll draw the loop in green. This is kind of like an x-ray of this. It's kind of in the middle. And we're given a bunch of stuff, and we want to find basically the amplitude of the EMF induced in the loop. So the current through the solenoid is time dependent. And so as always, we want to evaluate E is the EMF. So that's just minus number of turns in the loop, which is just 1, times the time derivative of the magnetic flux. And the time derivative of the magnetic flux is, so we need to find the magnetic field and multiply it by the area. So I'm going to kind of step back from this now that we have the main framework of the problem, i.e. this one formula. I'm going to write down the given. So we're given the area of the loop is 6.8 millimeters squared, and then we want to convert that to meters. So we want to divide by 1,000 millimeters per meter squared. And the number of turns per unit length of the solenoid is 854 times 100. Again, it's in units of turns per unit centimeters, so we want it in turns per unit meter. And our I is 1.28. So it has an amplitude of 1.28 and sinusoidal, so I'm just going to say that it goes as cosine, although it could equally go as sine, times with an angular frequency omega, so it's just going to be cosine omega t, because that's the form of sinusoidal oscillations, and that's already in radians per second, no unit conversions needed. So this is all the information we need. So EMF is going to be minus the time derivative of the magnetic field, or the magnetic flux. So we need the magnetic field times the area. So the magnetic field of a solenoid is mu naught number of turns per unit length times I of the solenoid, and then times the area. The area and the magnetic field are aligned, vectors are aligned, and therefore we don't have to worry about any dot product angle cutting the answer down. So just in conclusion, it's just going to be B times the area. What's changing with this? Everything's the same except for the I. And so therefore we can say that it's equal to minus mu naught N A times the time derivative of I. And then to get the amplitude, we just need to find the maximum value of this. So let's just kind of evaluate that on the side. So di dt is going to be 1.28 magnitude, 1.28 times 212 times the sine of 212t. Yes, I used magnitude, so I didn't have to write the negative sign. Very clever, huh? Okay, great. So that's the time derivative, and if we want to get E amplitude, we just can, we just cut this sine part. And so then therefore it's minus mu naught times N times A, and then I'm just going to write out this number instead of creating a variable for it. So that's 1.28 times 212. And then mu naught's minus 4 pi 10 to the minus 7. N is, okay, I'll use NS. Fine, I'll be consistent. A is given by this. And then when I put that into a calculator, I got a very small number, 0.000198 volts.